So under this module, we are going to be looking at the power transformers, their common problems and their remedies. So as we all know, the power transformers, they are very important piece of equipment in the power system. So we are going to look at some of the associated problems during normal operations. So what could cause those problems and the possible remedies to those problems and how we can prevent such problems from occurring in the course of the operational life of the transformer. So like we said earlier, the transformer is a very important piece of equipment in the power system, and anything that affects the transformer will affect the entire power system, especially the part of the system that is connected to it downstream. Okay, so as you can see on the screen, you see that right from the point of generation, we have the transformers that amplifies or step up the input voltage to a transmission voltage, and then before it is fed to your consumers or the users, it is stepped down, and what is needed, it is also the transformers. And then at the final point of utilization, especially at residential areas, okay, we still need the transformer to step it down to the voltage that could be used at the various homes. So you see that the transformer is a very important piece of equipment, and as you can see, if anything affects any of these components of the power system, which is the transformer now, it will affect the entire power system, especially the part of the system that is downstream, as we said earlier, of the transformer. So as we said in the introductory aspect of this module, we are going to be looking at some of the common problems or common faults that we may encounter in the course of the normal operational life of the transformer. So the first that we'll be looking at in this module is problems that are associated with the windings. As you well know, the transformers, they have two sets of windings, the primary and the secondary. And the winding is the active part of the transformer, and anything that affects the transformer winding will affect the operations or the output from that transformer. So we are going to be looking at some of the associated faults and how we can possibly prevent such problem from occurring, and also prevent determine when they are happening, and see how we can remedy the situations. So the insulation, we know that the primary and the secondary windings, they are separated. Okay, as you can see, they are separated. You don't expect them to have any connection or contact with each other. So what is separating them is the insulating materials, and even each of the windings, as we'll see later, they are the conductors in the windings, they are also insulated from each other or one another. And then as you can see also on the screen, whichever winding is wound first on the core of the transformer is also separated by an insulation. Okay, that is, there is an insulation separating the core from the windings also. So we are going to look at some of the problems that will be associated with the transformer insulation, and also how we can determine when they are happening and remedy those problems. So we also have those that are associated with the tap changer. As you can see here, we know the tap changers, they are mechanical devices. They are meant to regulate the voltage output from the power transformer. But at times, some problems, by virtue of the nature of its operations, some problems might result or might come up. So how do we know when such problem is developing and how we can possibly take care of such problems? We're also going to see all of those. Then the bushing too. These are the bushings. They are insulators. They are insulators that are meant to guide the conductive part and prevent the conductive part. Okay, guide the conductive part into the transformer and to prevent it from having anything to do or come into contact with the body of the transformer. So it guides the conductive part straight into the transformer before it is connected to the windings. So the insulators, that is the bushings, they are very important component on the transformers too. Failure on any of the bushings can result to grounding fault on the transformer, and that will definitely shut down or destroy the transformer. So we are going to look at some of the problems and how we are to take care of them. Then lightning strike. Though this is not a fault per se, is an event, but it has the effect of introducing fault into the transformer system. Because lightning strike, they can induce transient overvoltages into the system, and these overvoltages can stress the transformer windings beyond its capacity and thus destroying the insulation of those parts that it flows through. So we are going to see how we can prevent lightning strike from affecting our transformer during normal operations. Then line faults too. Faults could be introduced on the lines that can affect the transformer. We will also see all of this. And finally, we are going to look at the mechanical faults. Faults that are associated with the tank, the cooling fins, okay, the oil pump, the Bucos relays, and even the conservator tanks, the cooling fans. All of these, we are going to look at them also and see how we can prevent such from affecting the transformer operations. So without wasting much of our time, we are going to be looking at the first one now, which is the winding faults. Winding faults. Remember, we said the transformer winding is the active component of the transformer. That is where the transformation is done, the changing of the voltage from one level to the other, which is what we needed out of the transformer. That is, if we are looking at step up, it will step up the voltage. If we are looking at step down transformers, it will step down the voltage. So these windings, faults can develop in them or occur in them during normal operations. So what kind of faults do we think are associated with these windings? So the first one that we are going to be looking at is the turn-to-turn fault. Turn-to-turn fault. Remember that each of the conductor that is used to wind the transformer winding, either the primary or the secondary winding, is insulated, as you can see here. Okay, there is a conductor inside this insulation, so it is insulated, which means that these two strands that you are seeing, these two conductors, you don't expect them to have any contact. That is, electricity that is flowing through this cannot go into this one, even if they have physical contact. Okay, they will not have electrical contact. So that is how it is designed. But because of some fault condition, you see that this insulation could be broken. So once this insulation is broken, this turn will be shortened to this turn, and thereby reducing the effective resistances of the entire transformer, and can even affect the transformation ratio of the transformer. So the turn-to-turn short is one fault that can affect or that can happen in the winding, transformer winding, that can affect the operations of the transformer. Then the other one that we'll be looking at is the phase to phase short. Okay, so like the first one, the turn to turn short can happen within each of these phases. In a transformer, we have three phases, as you well know: one, two, three. So the turn to turn short, which is the first one that we consider, can happen within each of these phases, either in the primary or in the secondary. Okay, but in the case of the phase short, is an interphase short, short between this phase and this phase, which can also result because of the failure or breakdown of insulation separating both phases, either at this connection point or within the transformer itself. Okay, so that can affect the transformer, and we know that face to face short like that, they are usually very high current event, and that high current event can overstress the winding of the transformer and cause burnout. In the case of turn to turn short, it can result to arcing. That arcing over time will increase the temperature of the transformer, can cause the deterioration and eventual failure of the insulation, okay, surrounding that area, and cause overheating of the cooling oil that is within the transformers. So you see that both of these events, they are not desirable at all, because each of them can result to the burning of the transformer winding and eventual shutting down of the transformer, which will affect the system reliability and availability of the entire power system. So the possible causes could be that, one, during manufacturing, proper care, okay, was not taken, or standard operating procedures were not adhered to during manufacturing. That is one. Or substandard materials could be used during manufacturing. The right gauge of conductor, that is the wire now on each of the winding, is not used. The right insulation or insulating materials, they are not also used. Okay, so all of those can introduce defects that will show up during normal operations. Then the second one is overheating. Remember, each of these insulations, they are designed to withstand a level of heat during normal operations. So once you go beyond that level of heat, it will cause deterioration in the insulating materials, and even the conductor itself. Each of them, they have their own current carrying capacity, okay, which affects the heat or the temperature in the environment in which it is operating, can also affect that current carrying capacity. Remember, during normal operations, it generates its own heat. And then once overheating occurs, that means the heating will be more than what is normal. And that can cause deterioration of all of the components, all the materials within the transformer, the winding, the insulating materials, everything. Okay? And then result to eventual failure. Mechanical stress too, which may be as a result of overheating, excessive current maloperations, okay, can cause problems too, or can result to winding failure. Remember, the heating, either the heating is caused by electrical current flowing through the conductor, or overloading, which is also the current caused by the current that is, which will also result to overcurrent that will cause overheating. Okay, such overheating causes expansion and contraction of each of these components, be it the conductor or the insulating materials that is used in the production or manufacture of the transformer. So this expansion, constant expansion and contraction can cause mechanical stress, especially if it is stretched beyond its mechanical limit, okay? The limit that it can actually withstand, where it can no longer gain its normal size or its normal strength, so to say, after contraction. So, or rather, after the transformer has cooled down. So, such mechanical stress caused by frequent expansion and contraction can also result to those turn-to-turn short or mechanical failure. Though proper workmanship during the stage of manufacture or reworking, rewinding can prevent all of this. Then finally, aging. As we all know, all of these components, as they age, they deteriorate. Their insulating capability goes down. All the insulating materials, the dielectric strength and what have you, all of them, they deteriorate. And as they are deteriorating, of course, any of these problems can result. So what are the ways that we can use to determine winding fault as they are happening? Remember, the winding is an internal component of the transformer. They are inside the transformer tank. So it's not something that you can access from the outside. So how do we assess, or how do we know if such problems are happening within the transformer? Okay, that is in the winding within the transformer. So remember that each of these transformers, they have insulating oil that is meant to cool and to insulate the transformer itself. So this transformer oil, since it's having a direct interaction with the winding, it is possible that we can look at the oil to determine what is actually happening within the winding. So what we need to do is to carry out oil analysis, okay? Oil analysis to determine the dissolved gas that are within the oil. Remember, one, that the oil is made up of hydrocarbons, okay? So it depends on what is happening within the winding as it is heated up either by virtue of its normal operations, or when there are fault conditions like arcing, shorts, overheating due to excessive current flowing through the transformer windings. All of these can cause the decomposition of those hydrocarbon molecules within the transformer oil. Okay, so these hydrocarbon molecules, on dissociating, the product of dissociation is actually determined by the kind of fault that is within the transformer. Here are some of the product of decomposition of the oil, or interaction of the oil and the heat or fault condition within the transformer. We have hydrogen. Remember that when we have high thermal event like arcing within the transformer winding, okay, that can cause the dissociation of the hydrocarbon molecule, producing hydrogen gas. So that hydrogen gas is a clear signal that there is an electrical fault within the transformer. Then we can have moisture also within the transformer as a form of as a byproduct of reaction of the mineral oil or the hydrocarbon in the insulating oil in the transformer. So moisture can also be introduced when our silica gel, okay, on the breather line in the transformer is not functioning properly. as we explained earlier in one of our videos on in one of our trainings on transformers. Okay, so that can bring in, as the transformer is breathing, if the air that is coming from the atmosphere is saturated with water vapor and the silica gel is not able to capture those moisture, okay, at that point it will go into the tank and that will condense into the oil. And once we have moisture in the oil, what will be the effect? It will reduce the dielectric strength of the oil, that is the insulating capacity or capability of the oil, and thus causing short, okay, where it is not supposed to cause short, and problem in the winding of the transformer. So we also have other compounds that will be released: carbon monoxide, carbon dioxide, methane gas, acetylene, ethylene, and ethane. Okay, all of these gas, they are signs. If you see them in your transformer oil, they are signs that something heinous is happening within the transformer. So what we do in this case is to sample the oil. Okay, we have sampling points, as you can see the on your screen. We have sampling points where we take oil samples and then we take it to the lab. If it is we have oil analyzers that we can use in situ. We take the sampled oil, put it into the analyzer, and it will give us the percentage composition or the composition in parts per million of all of these dissolved gases. So as we are trending, we will be able to see a pattern, especially if it is increasing. Okay, so if it is increasing, that will tell us clearly that something is happening. So here is a chart showing us the various gases that we could come across within the transformer oil during normal operations. Okay, and then the level that will tell us clearly that fault is already developing within the transformer oil. So if you look at this, you see here we have hydrogen, we have methane, and all other gases. Okay, and even the combustible gases that may be in the oil. So if we take that of hydrogen as an example, H2, so once the concentration is less than 150 parts per million in the oil sample that we take, of course that is within normal limits. Okay, but once it gets to that 150 and is climbing beyond that 150 parts per million, that is an alarm level. So what this means is that we should increase the frequency of our monitoring and bring all other condition monitoring technology to help us to ascertain what is actually happening within the transformer. That is, we want to check to see the cause of that increase. So that's the alarm level, and in our instrumentation on the transformer, we can set the alarm level at that 150. So once it is 150, is indicated in the control room, we are signaled that the oil, the concentration of hydrogen is going beyond 150 parts per million. Then if it rises beyond 1,000 parts per million, that means the transformer should shut down, because what is causing it has become severe. Okay, so we can configure our instrumentation to shut down the transformer at this stage once the concentration has gone beyond this 1,000 parts per million. So what could be the possible cause of hydrogen gas? You see, corona, arcing. Remember, we also have the Bucos relay that will help us to also look at this, because as the the concentration of hydrogen is increasing, the amount of gas that is generated that will go through the bucous relay to the conservator tank, okay, it will be increasing. So as that rate is increasing, it can also trip the the transformer, or it can signal an alarm if it is not up to that trip level. So methane gas, the possible causes, they are sparking, as we'll see later. Even little coronas, okay, they can result to all of those, the emission of methane gas. Acetylene, arcing, then overheating, ethylene. Overheating can result to the emission of or the production of ethylene gas. Then local overheating that could be caused by turn to turn short, okay, or partial discharge can all result to the emission of ethane gas. Severe overheating and overheating also, okay. So we can use all of this chart as a guide to indicate what is actually happening within the transformer. So the next that we are going to do is the partial discharge test. When we say partial discharge test, that is, there is it's not full short, as in the case with the turn to turn short that we saw earlier, that we discussed earlier, okay. So but there is a partial discharge because of weak insulation between the turns or between the windings. So the current at times may, since the insulation is weak, may want to jump, okay, shorten the shorten the circuit or the winding of the transformer. So that partial discharge, we can test for it if it is happening before it will deteriorate to the level that it can cause corona or serious arcing that may eventually destroy our transformer. So we can test using the ultrasonic testing equipment, fix it on the transformer tank and listen, because this partial discharge is a very high frequency event, okay, that happens within the ultra high frequency range that could be detected by those ultrasonic detectors. So we can also use radio frequency detectors too, to listen for the audible sound that are coming from the tank. If there are partial discharge, it will be distinct for us and we'll be able to. So these are some of the ways that we can use to detect winding fault since it's internal, okay. So all of these are condition monitoring techniques, the dissolved gas analysis, the partial discharge testing that we can use in determining the condition of the transformer winding. So how do we prevent the transformer windings from developing faults, turn to turn shorts, face to face shorts? Okay, so the first is to adopt good quality control, standard quality control during manufacturing. Use the right material for the production of the equipment. The insulators or the insulating materials all should be of the right class, insulation class, for that operations for which we want to subject the transformer to. Then also the conductors that we'll be using, we use the right gauge so that it will be able to withstand the expected current, the maximum current that we expect on the power system, okay, in which that transformer will be connected. So good quality control during manufacturing is the first step. Then regular maintenance is also very important. Regular maintenance of the transformer and also of the line or load to which the transformer is attached. That is also very important. Do oil change out when the oil is due for change out. Regular inspection of the mechanical component, as we'll see later. the other accessories on the transformers, the cooling fans, and what have you, the current transformers, the voltage transformers, regular monitoring and maintenance to see that they are actually delivering what is expected of them. Then the protection system too, which is what the current transformer and voltage transformer, in most cases apart from indication, will be used for. Okay, so they are tied to the protection system. So we want to have an effective protection system. Remember, if the winding is overloaded, the transformer is overloaded, can result to heating that can cause some of the problems that we discussed earlier before. Okay, then if the problems are happening, how do we know that such problem is happening? Of course, we know that face-to-face short is a very high current event that can that high current event can result to tripping of the transformer if we connect it to our protection system. Then the arcing, even if it is turn to turn, all other thermal event that can result to all of this generation of all of these gases, our Bucos relay is there also to help us to shut down the transformer or to tell us that the rate at which this gas is generated is increasing. Okay, so as they are going through. So we also want to be looking at, that is, maintain a regular maintenance schedule or inspection schedule of the silica gel, okay, on the transformer to see if it is saturated or not. So if it is saturated, we want to change the silica gel, because once it's saturated, it means that moisture will be admitted into the transformer. So we want to, for very large transformers, once the saturation gets to a level, okay, large and remote transformer, that could be indicated in the control room so that we go for silica gel change out. So still on the common fault, we are going to be looking this time at insulation faults. Remember, we said we have three set of winding, that is one to each of the phases. For each of these sets, we have two different windings, primary and secondary windings. Okay, and then, like we said before, this primary and secondary winding, they are separated. As you can see, they don't have any connection with each other. Then the one that is wound inside the winding, that is closest to the core, okay, is also separated from the core, does not have any business with the core. The only business that the primary and secondary winding have is at the connection point, at the start point or data point, okay, outside. That is electrical connection, no physical connection. That is what we are also seeing here. This is the core. You see that the winding inside, if this is a step down transformer, if it's a step down transformer, here we'll have the secondary winding, okay, because the lower voltage winding is supposed to be closer to the core. So this is the core. This is the insulation separating the secondary winding now. This is a step down transformer from the core. Okay, so the core and the primary secondary winding does not have any business, or the winding of the transformer. Then the secondary and the primary, they also do not have any business except at the point where we deliberately make those connections. That is the connection points. Okay, so these insulations, remember, they have dielectric strength to withstand the voltage level to which they will be subjected to. So, but over time, as we saw earlier, deterioration can set in. Okay, maybe due to operational problems or due to old age. So once this deterioration sets in, the insulation will start failing, and once it fails, it can cause all of those winding problems that we saw earlier. Okay, so this is what we are discussing. Each of these conductors on each of the windings, they are insulated. Then this is the core, this is the insulation. This is where we have the core to come in later. Okay, then this is the secondary winding. If it's a step down transformer, you see that we have an insulation that will separate the core from this winding. Then if you look at this, these are separations. Okay, it is meant to separate the primary winding from the secondary winding, that is the high voltage side from the low voltage side. So those are the insulators that we are talking about. Then what could cause insulation failure? Not using the right insulating materials, that's materials of the wrong insulating class, can cause insulation failure. Or not adopting standard manufacturing processes can also introduce defect into the transformer at the end of the day. Then overheating, like we said before, overheating have the effect of stressing these insulating materials, and once it is stressed beyond some level, it will not be able to recover, and if it does not recover, it can cause failure of the insulating materials. Then mechanical stress too, as we discussed earlier, rapid expansion and contraction can also result to stressing the insulating material. And of course, age can also result to deterioration of the insulating material. So we are going to be looking at another area where we could have possible problems during the normal operations of a transformer. This time we'll be looking at the tap changer. So the tap changer, as you well know, is a mechanical device that is meant to assist us in regulating the output voltage from the transformer. This is the tap changer, okay, on this particular transformer. So it's basically a switch. So, and we know that switches, they have contacts, okay, they have contact, and during switching, that mechanical operations can cause the wear and tear of that contact. And since we are looking at electrical load on that switch or on the tap changer, okay, usually we have it on the high voltage side, because that is where we have the reduced current or lower current. Okay, so once the contact have deteriorated, which means that it will not be able to make proper contact, firm contact, that will result to partial contact at those contact points. So we know the effect of partial contact in electrical system. That can result to arcing, that can result to burnout of those contacts. And we know that arcing is a very high thermal event, have the effect of increasing the temperature of the insulating oil that will be covering the tap changer. Okay, so and what we also discussed earlier can result to the generation of those gases that we saw earlier, hydrogen, methane, and what have you. And once those gases start generating, it can go through the Buckhorst relay to the conservator tank, because naturally, since it's gas, it's lighter, it will rise up. So as it's going through to the conservator tank through the Buckhorst relay, that can cause the shutdown of the transformer. So basically, most of the time, the problems that we have with the tap changer, they are mechanical issues, wear and tear on those mechanical contacts, okay, that will result to arcing or burning of those mechanical contacts. So there are times too, remember, that if the tap changer is an unload tap changer, which means we may have a system that will help us to be changing the tap while the equipment is unload. Okay, in most cases we have a motorized system attached to the end of the tap changer that helps assist us in changing the tap. So if the control system to that particular motor is faulty, of course it can result to either not turning the tap changer appropriately, or even an outright failure. And if it does not turn it appropriately, it can result to also partial contact that can create problems in the system. So how do we remedy issues or problems with our tap changer? First, during normal or routine main ten ance, we want to do minor adjustments and cleaning. Okay, because if there are debris on those contacts in the tap changer, it can also result to those problems that we outlined. We carry out minor adjustment too. Then if we see that it has worn beyond a level, because the manufacturer will recommend tolerance limits, okay, of the clearance between each of those contacts. If the tolerance limit has been exceeded, of course we want to replace either the parts that is worn, or we replace the entire tap changer or the overall unit. Of course, there are some too that we can refurbish. Remember, it is cheaper to refurbish if we have good repair facilities around. So we can refurbish those tap changers. So another very important area that we will be looking at again is the bushings. The bushings on the transformers. Remember, the input power comes into the transformer through the bushing and goes out, output power goes out of the transformer also through the bushings. So we need to guide the conductor that is carrying the power into the transformer such that it will not have any contact with the frame, or that can result to grounding, okay, making the transformer dangerous and introducing fault condition into our power system. That is something that we do not want. Okay, so bushing faults. What can cause bushing faults? One, remember the bushing is made up of insulating materials that will be able to withstand the voltage of operations of that particular transformer. That is the voltage that is coming in, and on the output side, the one that is going out. And then if we have water ingress into the bushing, as you can see, if assuming we have water ingress into the bushing, this is the conductor. So that water that comes in can have the effect of reducing the insulating capacity or capability of the bushing, and that can cause shorting to ground. That can trip your transformer if you have ground protector in the transformer, or can cause severe safety problem or safety risk to operators or workers in the facility. So moisture can ingress when these gaskets, okay, is bad. So we can have moisture into the bushing. Then of course aging can cause deterioration, or the environmental stress on the bushing, okay, can also introduce or result to deterioration of the bushing, causing the dielectric strength of the material used in producing the bushing to go down. Then manufacturing defects too can also result to bushing faults. Okay, if there are manufacturing defects that compromises the dielectric strength at some points, within the transformer. Maybe we have voids within the bushing. I mean to say, if we have voids in the bushing, that can drastically, or air trapped within the bushing material, that can result to reduction in the dielectric strength of the bushing. So mechanical damages or mechanical damage, if there are cracks on the bushing, okay, that crack can serve as vent for the escape of that high potential that is flowing through the middle of the bushing. So, and that can cause it to flow to ground too. So deteriorated insulation, maybe due to age, can also result to all of these problems. So the bushings, they are very important component of your transformer, okay, and thus making it also very important in your electrical power system. So we are going to look at lightning strike. Like we said earlier, lightning strike is not a fault per se, but it has the capability of inducing fault condition. Remember, lightning strike can result to voltage spikes, okay, transient over voltages that will be beyond the holding capacity of all of the insulating materials that you are using, that were used in, or that is used in the transformer. So if that happens, it can result to all of those problems that we outlined earlier: turn to turn short, face to face short, short to ground, and what have you. Okay, so that is why lightning strike is very detrimental, and we need to really consider it during the design and installation phase of our power system. So like we said before, it can result to winding faults. It can even result to bushing faults. Okay, remember the bushings, they are designed to withstand a level of voltage. Okay, the voltage pressure. Beyond it, it will break down the insulation of the bushing. And of course, the core, since the insulating material between the winding and the core has been broken, it can result to core problems, okay, in the transformer. So what are the possible remedies? What can we do to be sure that we, in the event of lightning strike, will be able to take care of every eventualities that may occur, okay? So the most common and most effective is the use of lightning arrestors. Lightning arrestors, that is what we'll see here. So it is connected to the line feeding the transformer, as you can see. So these lightning arrestors, they are made up of metal oxides, okay? They are non-linear resistors. When we say non-linear resistor, what we mean is that at lower voltages, the resistance is very high. Then as the voltage is going up, at higher voltages, the resistance is small, very low. At times, at some voltage level, it will just go to zero. So thereby creating very low resistive path, okay, for the current to flow through to ground. So these arrestors, they are connected to ground. So once you have lightning strike, which will eventually induce those transient over voltage, those voltage spikes on the line. So before it gets to, as it's flowing through, before it gets into the transformer to the winding, okay, since it is beyond the level for which the arrestor is designed, you see that the resistance of the arrestor will go, the metal oxide in the arrestor will go to zero, and then all the transient over voltage and the excessive current all will just flow to ground, thereby clipping the excessive voltage, okay, from flowing through into the transformer winding and cause problems within the transformer. Then good grounding too. Remember, all of this that goes through the arrestor will send to ground. Good grounding too can also assist us in preventing the effect of lightning strike. And of course, shielding, okay, will also assist us. Then we're still on the common fault. We are going to this time be looking at the line faults, okay, faults that are associated with the line. Remember, we said the input voltage comes into the transformer, and then the output voltage, that is the high voltage. If it's a step down transformer, the high voltage goes into the transformer by the input, and then the output comes out of the transformer. As you can see here, the input to the transformer, then the output out of the transformer. Okay, so if we have problems on the lines, any of these lines, assuming we have short on the line, what have we succeeded in doing is shorting the transformer winding also. Okay, and that can result to very high current event, excessive current event that can burn the transformer winding, cause deterioration of the insulating materials used for the transformers, and other faults. Okay, so that can result to short circuits, and then at times, if the arcing is high, it can cause the burning and eventual breaking of that conductor. Okay, and that will cause open circuits, either within the winding or on the line. If it is within the winding, that can cause the decommissioning of that transformer in the system. So what are the remedies? So we want to put protective relays, line protection on the transformer, so that if there are line faults, okay, short circuit faults, it will see it and then open up the breaker feeding the transformer. Okay, then we also can use fuses in non-sensitive and less expensive transformers to open up the line when there is line fault. Then we want to have proper line maintenance strategies in place, such that such faults, and of course operations too, good operations of the power system can also help to prevent all of this, and proper maintenance too, okay, will help to prevent all of this. Then lastly, on this module, we are going to be looking at mechanical faults, mechanical problems. We have considered the active parts, though we've also looked at some mechanical parts, but this time we are going to look at all other auxiliaries to the transformer. That is the tank that is holding the oil, the cooling fins, the cooling fans. Okay, all of these, they are mechanical components that can develop faults that can affect the operations of the transformers eventually. We know that the cooling system plays a very big role in the operations of the transformer. So if the heat that is generated within winding is not effectively evacuated, it will affect, as we have seen in the discussion on this module, it will affect the operations of the transformer. So that cooling system, if it fails, assume that we are looking at this cooling fan now. Okay, if the cooling fan fails, remember the function of the cooling fan is to force air through these cooling fins, thereby increasing the rate at which heat is removed from the fin, and thus the rate at which heat is removed from the transformer cooling oil. Okay, so if anything affects it, that means that rate of heat evacuation will go down, and that can cause the heating up of the transformer and the transformer winding. And remember, once the winding is heated up, it increases the resistance of those windings, the conductor, and the circle becomes very vicious, and that can result to eventual shutting down of the transformer, if not eventual burnout. Okay, Then the tank too, see there are gaskets at all of these points. If they are leaking, that can cause the shortage of oil within the tank, and once the oil within the tank is short, that will also result to ineffective cooling of the transformer and reduce insulation. Remember, the oil also serve as insulator within the transformer itself. Okay, so that can also cause reduced insulation. The oil pump too is another very important component if we have oil pump within the transformer. So if that oil pump is not effective, not transferring the oil from the tank to the cooling fins and back to the tank effectively, that can also affect the cooling system. Then another mechanical fault is vibration and noise. There are a few things that can cause vibration and noise. Remember, we have the lamination, the core. The core is usually laminated. Remember, it's not a solid core. Okay, so if it is not firmly gripped together or tight together, you see that during operation, because of the magnetic field that is generated, you see it vibrating, and that vibration will add to the mechanical stress on the transformer that will eventually result to high temperature or add to the temperature of the transformer. Another thing that can cause vibration too is maybe when we have unbalanced magnetic field on each of these faces of the windings, okay, in the transformer, which may be as a result of short within any of the winding. Okay, so that unbalanced feed, okay, that will result to them not cancelling out, can also result to vibration and noise. You hear the transformer overhumming, and overloading too can also cause vibration and noise in the transformer. So we want to guide against all of this. So how do we take care of this? One, we want to carry out regular inspection and regular maintenance of our system. Okay, we want to check the transformer to see that there are no leakages, check to see that the fans are all operating when they are needed to operate. Okay, check that even the fans, they are not vibrating unnecessarily, they are blowing in the right directions. Okay, then proper instrumentation too can also assist us. We want to have instrumentation that will be looking at the cooling system, looking at those fans, the oil pump, looking at their operations, and also looking at the level of the oil and even the temperature of the oil. Okay, so proper instrumentation will assist us. So thank you very much. That brought us to the end of this